But when changes do not disturb the equilibrium, well, if we add, remove, or change substances that are not included in the equilibrium constant expression, there's no change at all. So for example, if we have this equation going, and then we decide to add some sugar, I'll just say sugar here, or we can add sugar here, whatever, it's not going to have any effect on this equilibrium because it's not involved. It's just like, hey, whatever, it's just a bystander. It's like if you're making your sandwich, if we go back to the bologna sandwich here, the bologna and then the bread, and we're making a bologna sandwich. If you put a apple there, or if you put an apple here, the apple has no effect on making that sandwich. So it's not going to shift it either left or right. Nothing's going to happen. Now, what about speeding up the time it takes to reach equilibrium, such as adding a catalyst? Well, let's look at that. If we have reactants, go to product, a catalyst here, catalyst will just make the reactants produce the products faster. So instead of maybe 1 hour, it's 1 second. But that means the products can go back and make the reactants and reform the reactants just as quick. So the rate will be the same for going from reactants to products as products to reactants. So there will be no shift either way. Adding a catalyst will not have an effect. Now it's time to play Le Chatelier's Principal Party Game by Partymeister Le Chatelier Henri. Do you know he was out down to party? When Le Chatelier showed up, you know it was party time because he would always play. Name that shift. Okay, now let's guess the direction of the shift. What happens if we increase the concentration of a reactant? It's not a pure solid or liquid. Can we guess? Hopefully you guessed right. It is to the right. Okay. Hope you're keeping score at home. What if we increase the concentration of a product? That means it goes left to the reactant. Decrease the concentration of a gaseous product. Decrease the concentration of a gaseous product. That means it goes to the right toward the product. We make more product. We decrease the concentration of an aqueous reactant. We decrease the reactant. Goes to the left toward the reactant. If we increase the concentration of a pure solid product, nada, nothing happens. Remember, just concerned with gas and aqueous solutions. What if we increase the concentration of a pure solid reactant? If you were paying attention to the previous one, you should know nada. What happens if we decrease the volume of the reaction below? So if we decrease the volume of the reaction, it is to the right, the one with the less number of molecules. So the one on the left has 2 molecules. This only has 1 molecule. So remember, if we're decreasing the volume, we increase the pressure. We want to alleviate that pressure by having less molecules there. Alrighty, more fun. Increase the volume of the following reaction. So we increase the volume. That means we decrease the pressure. Nothing. Why? Well, remember, number of molecules. There's 2 molecules here, 2 molecules here. 2 on this side. So there's 2 total here, 2 total there. So nothing happens. How about if we increase the volume of the following reaction? Increase the volume, decrease the pressure. Right. Because if we decrease the pressure, the one with the most molecules, there's 2 molecules here, 2 moles, and 1 molecule there. So it shifts to the one to increase the pressure. Add a noble gas to the reaction to increase the overall pressure. Nada. It's not part of the reaction. Noble gases are not part of the reaction. They don't do nothing. Just like if you're making a sandwich and you add a yo-yo. It's not going to do anything to the reaction, not anything to the way you cook. Increase the temperature of an endothermic reaction. Okay, if we increase the temperature of the endothermic reaction, we're adding heat. So it goes to the right. Since we have to put more energy into that reaction, and we're going to get more energy out of it. How about if we decrease the temperature of an endothermic reaction? Well, we can probably make a guess here. Left. Okay, that means we're putting less energy into the endothermic reaction, so it's going to stay more in the reactant realm. If we increase the temperature of an exothermic reaction, well, that means there's all this extra heat out there, so that means we're going to shift it to the left. And if we decrease the temperature of an exothermic reaction, it's colder outside, we're going to want more energy, so we're going to make more product. Right. How about if we add the catalyst? Nada. Now let's look at the equilibrium constant. K equilibrium. This is the ratio of product concentrations to reactant concentrations that are at equilibrium. Now what does this tell us? What this tells us is if K equilibrium, the equilibrium constant, is greater than 1, the products are favored at equilibrium. So there'll be more products at equilibrium. If there's less than 1, then the reactants will be favored. So there'll be more reactants. And the way we can figure out what the the equilibrium constant is by this equation. So what does that mean? C is the concentration of a product raised to the power of the mole, or the coefficient, times the other concentration of that product raised to the mole, of that coefficient, divided by the concentration of the reactant raised to the power of the coefficient times the concentration of the other reactant raised to the power of that reactant's coefficient. So really we're just plugging things in. Concentration will be in molarity, which equals moles per liter. So that's what a concentration by these brackets just means, a concentration, which is moles per liter. So if you're given the molarity, we have the concentration. Let's try a problem. So for this reaction, and we're given concentrations already, well, let's find the equilibrium constant. So remember the equation, equilibrium equals C raised to the C power, the concentration of that, times D raised to the D power, which is the coefficient, over the concentration of reactant A raised to the A power times the reactant B to the B power. And we can say this is A, B, C, which is basically NO, concentration of NO, over N2, concentration of O2. What about D? Well, there's no D, so we don't have to worry about it. Now, what about the reactants, or the coefficient, what about the exponents here? What's raised to? Well, there's no coefficient, just 1 here. I mean, we don't put 0, but we just put 1. NO is 2, so we square that. And what do we fill inside NO? So N2 is 0.48. So we have 0.48 times O2, which is 0.75, and NO, which is 0.0030 squared. What does that come out to be? So we get 2.5 times 10 to the minus fifth. That means a K equilibrium is much less than 1. That will favor the reactants.